All right. Hey, everybody. Uh, Welcome back to week 8 of Fastbook Reading Group. I don't know why I said that in a robotic voice. But anyway, welcome back to week 8 of the Fastbook Reading Group. And I'm so excited for today. Today, we're going to be wrapping up chapter 6, and we're going to do live coding. I always dread live coding. So if things don't go well, bear with me. But I'll try my best to do the best of my ability. And then we'll be using Fast AI for Kaggle's Cassava classification competition. So we'll learn what the competition is. We'll look at the problem statement, and then we'll use Fast AI to find a solution for it, or to build a model that can do leaf classification. The main idea, like, it wasn't planned. It's just something 7 or 8 hours ago. It just occurred to me that it just occurred to me that this week is going to be a little bit different. Like, instead of going week after week, chapter after chapter, I felt that this is a good time to take a break and apply what we've learned, because that's really important. I think in your journeys as deep learning practitioners, applying what you've learned so far will bolster the understanding. It will make the understanding even better. And when we apply things to a new problem, we face challenges that we wouldn't have otherwise. And then in trying to find solutions to those challenges is where, like, the real growth and the real learning sort of happens. Because then when we're going to use cross entropy loss now, or like we're going to try and build the data block API, or we're going to build data loaders for a new competition, then we're going to have a deeper understanding of each of those concepts. And that's the idea. So that's why we're going to wrap up regression. And that's chapter 6. That's what was left. And then we're going to look at the Kaggle competition. So I think we'll have about 30 or 40 minutes of Kaggle live coding. So we'll see how that goes. Fingers crossed. As is usual, if you go to that link, wandb.me/fastbook8. So let me post that in the chat. wandb.me/fastbook8. So if I go to that link, that should take me. One second, I'm just bringing my browser. Can everybody see my browser okay? Could you maybe just give me a thumbs up in the chat? If the screen's too, screen's too zoomed out, or like if it's hard for you to read text, could you maybe also post in the chat that it's hard to read or zoomed out? Yes, a bit. Okay. How is that? Is that better? Is that perfect for everybody? Bigger, please. Okay. How about that? Okay, excellent. Cool. So we'll keep at that. What is that? 133%. All right, we'll use that zoom just because the screen resolution is a bit bigger. So it's hard for me to see how other people see the screen. Okay. So that's where we'll go. So any questions that you have, we're going to my focus then today. I'm really excited for what's coming next, and especially the Kaggle live coding part. So I'm gonna try and wrap up regression pretty quickly, and then I'm going to go to Kaggle Cassava very quickly. But then before we do any of that, this week has been super amazing. Something I did want to say is, like, a big thank you to everybody who's been writing blog posts week after week. And the one thing I feel is, like, the main idea for starting this Fastbook reading group was to make sure that whoever's on this journey starts this journey. But as Jeremy also said in the very first session, like the beginning, which we called Fastbook session 0, when Jeremy was talking about Fastbook and he was talking about Fast AI, what Jeremy said as well was that it's important to finish. And that was the idea for me as well. Like, being on this journey, there's a lot of time and energy that's spent in making these weekly sessions happen. But when I see the feedback loop, or when I see, like, people going and writing good things and then understanding like cross entropy laws, tweets being retweeted by Jeremy, tweets being loved by the Fast AI community, Zach Mueller being involved, or like Sanyam being involved, or like basically, I'm sorry if I missed anybody's name, but the idea is not to name names, but mostly to say like it's really lovely to see the whole community being coming together and being a part of this. So thanks everybody who's been writing, and I hope that by writing you're also benefiting from it. Like what I do feel is if you're on week 7 and someone who wants to go back to week 2, then you have your own notes which could be referenced. So I think that's a really powerful thing to have, is to have your own notes handy. And then it also makes it a really powerful thing to be active in public. So publicly sharing your work is definitely leads to job opportunities, definitely leads to really good things happening. So that was just a small thing that I did want to say before sharing everybody's work. So Ravi, thanks for coming back this week again and writing about the Deep Learning for Coders chapter 5, and really good quick recap on that one. Anand, loved your blog. It was shared just very recently before we started this session, so I couldn't read the whole of it, but whatever I read, I really enjoyed it. So thanks for sharing your work about and providing a summary of chapter 5. Akash, this I did read that this blog as well, and loved the way how you used maths. I think this is I even shared this on Twitter, that this is a really good summary of SGD, Nesterov momentum, and basically gradient descent in general. And this was really lovely to see some nice figures coupled with a bit of math. I would also add a bit of code in there, which would then make this like the only place where people have to be. So then your blog's going to be like complete. Nobody else has to go anywhere else. But really love this blog. Thanks for sharing. Thanks, Niazi, coming back this week and writing about chapter 5. I love the way you write, and thanks for summarizing everything that we covered last week. Korean, you're standard. You come here every week after week, and I only have to say thank you for coming back to this week again and writing about chapter 5, and then sharing your learning logs with us week after week. Vinayak, this is, I have to say, I was really impressed by Vinayak's blog on the Learning Rate Finder. I think he's gone in and he's basically shared he's basically shared his experimentation about the various learning rates, which I kind of really enjoyed reading. Like, it's not just about a theoretical blog that explains what things are, but it's also more like it has experimentation and it has really good things. And this one, I think I did share on Twitter. I just wanted to quickly point out that I'll bring up Twitter very quickly. And Zach, I think, pointed out to some resources as well. So this is something I did want to point out, is that Zach has said that he's made some updates to the Learning Rate Finder. And in fact, the new Learning Rate Finder looks a tiny bit different. So as you can see, now it has all of these Ella, Finder, Valley, Slide, Minimum, Steep. So in case, Vinayak, you want to go back and update your blog with this latest version of Learning Rate Finder, feel free to reach out to me or Zach if you have any questions. But again, thanks for this wonderful blog. So that's it in terms of sharing the work. So let's then get straight into chapter 6. 1 second. All right, here it is, chapter 6, multicat. So where we left off last week, I think this is going to be super cool. Again, I just want to say I'm not reading. I can see there's plenty of messages on Zoom. If there's anything that you want me to read, please post in the wandb.me/fastbook8, as I'm not going to be following the Zoom chat. So with that being said, let's get started. So where we finished last week was we were looking at the multi-label classification problem. We built our data set, and by the time we ended up, we looked at how things are a little bit different for multi-label classification, in the sense that they can be multiple objects or they can be multiple classes in a single image. And then we saw how this is where we finished. We finished at 1.1.4. We saw how the data block is different, and this is how our data kind of looked like. You had file names. It was shared as a part of a CSV. So there was some talk about pandas, and then you have your labels, and then there's this is valid column as well that says or that basically defines whether your image is part of the validation set or not. So based on that, we built our get X, we built our get Y, we built our data block. And then we kept on going and we added things one by one. So we added the blocks first. So this was basically building the data block step by step. Then we had a look at how the labels for multi-label are different. So you can see how in this case, like there's only one that is one, but the main thing we looked at is like how this is one hot encoded, and this is a different way of representing the labels. And actually, let me run this notebook. I haven't run this notebook. So it's running now. And then we saw how the labels are multi-labels. Let me see if there's another example somewhere. I'm just trying to find an example where two of these are one. Here it is. So we saw how this is different. Like it has this category as being one, so that's the label that's present in the image, and this category as being one. We don't know what categories those are right now, but data sets have their own vocab that we also looked at. So that was the main difference, and that's why it is one hot encoded. Because remember, we looked at how if we present this as numbers like 3 or 5, then each of the labels would have different lengths. But one hot encoding them makes sure that the lengths are same for every label. So that's the main things. Then we looked at, okay, what category? We looked at a torch.where function that kind of tells us what category or like which index basically the tensor is value of 1. And then based on that, we can grab our indexes. We had a look at the vocab. So now you can pass in the index in your vocab and you can see, okay, that's the one, that's one. So let's keep going. So let me run those bits as well. So you can see how datasets.train looks like this. And then you can pretty much, I'm just going to run those. This is just a recap. So this is a different thing. Then we built our data block. We saw how having a splitter is different. We added our own splitter this time. So I'm just going to run that as well. And that was it. And then we finished building our data block using our own custom splitter that uses the isValid column from the data frame, does the random resize cropping as an item transform. And we can look at our batches. So this is what the batch looks like. So if I have another row, here we are. So this image has it's a really bad image. So let's see if there's another image that shows. Okay, this one. So this image has a dog and a person. So it's like 2 labels instead of being 1, but other images have like a bird and dog. So that's where we finished. So as let me see if I can bring up OneNote. Oh, sorry, because I'm using 2 screens. 1 second, I just need to duplicate my screens, because if I write on OneNote, it won't show up in the screen I'm sharing. So 1 second, please. All right. That's not what we want to see. Screen sharing has stopped because external display is disconnected. 1 second, I'm doing that again. Every time I do this, there's some issues. So I do need to update the way I share my screen. Sorry, bear with me. 1 second, please. Okay. That's good. Next is just need to now be able to share my screen. So share screen. Okay, can everybody see my screen again? Could you please maybe just respond in the Zoom chat that you can? Perfect. And we're back. Awesome. So where I lost my train of thought, but I was talking about multi-label classification. So let's go here. Now you should be able to see my OneNote, and then if I go to Fastbook, and then I can probably scribble on my screen and it will show up. Excellent. We're good now. Okay. So then the thing I want to talk about now is basically then the difference in multi-label classification is you have your labels that are one-hot encoded. So let's say that's how my label looks like. So let's say I have just 1, 2, 3, 4, 5 categories, which could be, my 5 categories could be dog, cat, horse, I don't know, fish, and human. Let's say those are my 5 categories. This is, we don't have to have numbers, but then you can say, okay, this one is here, cat is the second one, horse is the third, because I'm one-hot encoding them, right? So let's say I have an image where a dog is present and a horse is present. So then the label for this would look like dog, yes, cat, no, horse, yes, fish, no, human, no, right? That's how the label for this would look like. And now I want you to think of how the loss function for this image could look like. Because what's going to happen is when we pass this image through my model, right, it's going to make however many classes I have, it's going to make that many predictions as well. So it's going to make 5 predictions. So 1, 2, 3, 4, and 5. And the predictions are going to be like, because it's not softmax or it's not sigmoid or nothing. It's going to be like just floats minus 0.7, 1.2, or so on. And that's how the predictions are going to look like. And I need to find a loss function that can then compare. 1 second, that's again. And I need to find a loss function that can then compare. I'm calling these as those are my labels. And then on the right are my preds or my predictions. And I need to find a loss function that can then compare my predictions to my labels. Ideally, what we want our model to do is have this one as a high number. So high, this one as a low number, and then this one as a high number, because see, those are the corresponding labels. So those are the indexes where this thing is 1. And we can't really use cross entropy loss, because remember, cross entropy loss uses log softmax, or the negative log likelihood, which we covered before. And it's trying to pick one category. Like, that's really good for one category, but not multiple categories. So then how about this? Remember when we were doing our, how about this? How about defining a loss function as this? So I'm just going to quickly just put my labels and predictions together. 1, 2, 3, 4. 1, 0, 1, 0, 0. Those are my labels. And then I have some preds, 1.2 minus 7.1. I don't know, just some random floats, right? And I need to be able to. So that's my label. And that's my pred. So how about a loss function? Because we want these numbers to be high and then the other ones to be low. So we want a loss function. How about a loss function that says, at places where this is 1, we want the prediction. First of all, let's apply a sigmoid, right? What will a sigmoid do? We've already looked at a sigmoid. A sigmoid will convert all of these numbers between 0 and 1. So the higher the number, the closer it is to 1. So let's say it makes like 0.8, 0.01. I don't know, I'm just randomly making these up. Maybe this is like 0.6, and then this is again like a 0.8, right? And then, so the first step I do in my loss is, let's say I apply my sigmoid to the model predictions. And then instead of now comparing, I don't care about like just my raw logits. I'm going to compare my label with this sigmoid version of my predictions. So I'm just going to call this as sigmoid. Okay, so I'm going to compare those two instead of comparing my label and prediction. And what my loss function is going to say is, how about a loss function that says, places where, sorry, let me try and use a different color. Places where this is 1, correspondingly, this should be close to 1, right? So how about I say that I want the loss to be 1 minus whatever the number is at these positions, because I want them to be as close to 1 as possible. This is the MNIST loss. Remember when we were talking about MNIST and we were trying to find a loss function to classify 3s and 7s, then we talked about this like distance. So when I'm saying, okay, I want this number to be as close as 1. And if you're not 1, then my loss in this case would be 1 minus that number. So in this case, it would be 1 minus 0.8. And for this one, it would be 1 minus 0.5. Okay, so that's the loss for this one, and it's the loss for this element. And for everything everywhere else where this is 0, so let me use a different color. So everywhere else where this is 0, how about then in that case, the loss is just whatever this number is, because we want them to be as close to 0. So 0.01 minus 0 is just 0.01. So the loss in this case is 0.01, 0.6, 0.8. And now what the model is going to try and do, so see how this is my loss on the right. And now what the model is going to try and do is when we're going to apply gradient descent on this loss function, it's going to try and make this number close to 1, like these two, and it's going to try and make every other number close to 0 or like smaller numbers. So that's exactly what we want. So this is how we could train multi-label classification, and that's how the loss function looks like. And what I've just explained is the binary cross entropy loss. So you can see how this is what exactly you'll see in binary cross entropy. When you read this, you'll see, because we have, let me just show this in code. So I create my learner. It's giving me some warning, but ignore that. I can see how my activation, so the model, because I have 20 classes, in this example, I just had 5 classes. So my model output a vector of like however many times 5. In this case, because I have 64 is my batch size. So when you're rerunning the notebook, I would suggest that it's really important to then see why these are the shapes that they are in. So then it says, okay, 20, that means 20 outputs. And then if I have a look at my outputs, these look like these random logits or just the random outputs, as I said, in this case, the predictions. And then you, if you have a look at the labels, then these are the labels that's how they look like. And then we could define a binary cross entropy loss function like this. We could first take the sigmoid and then use the wherever the targets are 1, in that case, the loss is 1 minus my input, and the other places where it is 0, it's just the number itself. And then we could take the log and we could take the mean, and that becomes your binary cross entropy loss. So we could train a model. Again, PyTorch has the binary cross entropy loss function. So you could just, there's 2 ways of using the binary cross entropy loss in PyTorch. You will see PyTorch does things slightly bit differently. So PyTorch has PyTorch NN functional, where that's like where the things are like functions that can be called directly, or it also has things as classes. So NN.cross entropy loss in PyTorch. So that's the class. So either you can use it as the class or you can use it as a function. It's not a very big it's not going to be like a massive thing to learn, but just when you go back, have a read of this paragraph, and it will just say, okay, that's how you can do the same thing in different ways in PyTorch. So the most common way of doing it is using the class version. So I'm just going to call that, and we can calculate a loss. I don't have my inputs and my outputs defined. So where is my input and target? Are they even defined somewhere? Did I miss something? Yes, I did miss my input and target. So ignore that, ignore that. Okay. So then I could just, when I'm training CNN learner, my CNN learner in this case, don't worry about all of this stuff at the back now. I think I've just, okay, 1 second. Actually worry about it. What I'm going to do is go to my Fastbook and I'm going to reset. So what I'm doing now is I'm just any changes that I've made to my notebook, I'm kind of resetting them because that's why the input and the target were not defined. So I'm just using an updated version of this notebook, which is not very helpful. So now Jupyter is going to load the correct version of this notebook. So that's kind of a sidetrack. What we've used is called Git. So you can have a look at Git and kind of look at that. So see now we have the correct version, which is the original version. So where were we? We were looking at the binary cross entropy loss. So we had looked at the activation shape. We had looked at how the activations look like. We had looked like how binary cross entropy looks like. And now we can define our, okay, we pass in actives and Y. Got it. So you can pass in your, basically the model outputs, and you can pass in your labels, and then you can then calculate the loss. So we'll see how that loss is calculated. So that gives me my loss. Any questions on loss so far? Because next we're going to look at metrics. I also wrote a small post about training a pet breed using what we learned. Oh, I'm really sorry. I missed that, Rabi. Let's see that. Building a state-of-the-art pet breed classifier. Oh, thanks for that. I will definitely give this a read. Oh, you're using the latest version of LR Finder. That's amazing. Zach would be really happy to see this. Thanks for sharing. Which other loss function we can use for multi-class classification? I think go for binary cross entropy loss is the way to go for multi-class classification. I'm not sure if there's any other loss function. It doesn't come to my head right now. So mean squared error, but it might not be as efficient as BSE. Yeah, it doesn't come to my head straight away on any other loss function. Why would you want to use a different loss function if binary cross entropy works? Okay, so then the next thing is, let's have a look. So now when we want to calculate the accuracy, because now what's going to happen is, let me again use my OneNote and bad handwriting to explain everything. Now my, let's say I have still the 5 classes, and my predictions are going to look like this, right? 0.3, 0.8, because remember, I have applied softmax. Oh, sorry, sigmoid. So, and my labels will say like this. 1, 0, 1, 0, 0. So now what we want to do is we want to compare the accuracy between my predictions and the labels. And I couldn't just, we can't use the accuracy that we looked at when we were doing single label classification, because that just takes the argmax. So what that does is it will find the argmax, just means like find the point where the value is the highest, and then compare if like, or like, then you get the class ID, and then you compare that class ID with the actual label. So if the class IDs are the same, then your prediction is accurate. If they're not, then it's inaccurate. But in multiple label classification, because you have multiple labels with one, what you have to do is you use something called a threshold. Okay. So you could have like, you could say, like, you could define your own threshold, and the threshold could be maybe 0.5. So anything that's greater than 0.5 is 1, and anything that's less than 0.5 is 0. So this then gets converted to 0. The second one, 0.3, gets converted to 0. 0.8 gets converted to 1. This is 0, and this is 0. And now you can compare this with this one, and you can calculate the accuracy. So that's exactly how things are a bit different. So in accuracy multiple, you just have your inputs greater than threshold, which converts things into a Boolean like 1 or 0. And then you can just compare it to your target, and you can see how many times you're correct. And then you just take the mean. So that becomes your accuracy. This is just a side note about using like partial functions. You'll find partial functions really handy when you're using deep learning in general, or just this is just a coding trick, you can have like your argument as some default value, and then you can then apply that a partial. I won't go much into the detail of partial. Have a read. It should be pretty straightforward. So then in metrics, you just pass your accuracy multi, and in this case, you're passing a threshold of 0.2, and away we go. We can train, we can validate, and we can then get our predictions. We can then create like a graph, because we're trying to find a good threshold. So we can see at which threshold what my accuracy values are. So then I'm trying to find a good threshold, and that's basically it. So if you go back and read this, I think then that should be really clear. So before moving on to regression, I did say I'll try and wrap up regression in 20 minutes, but I spent 30 minutes explaining binary cross entropy loss. So I'm really sorry for that. But let me just see if there's any questions on binary cross entropy. By the way, I have a feeling that today's session is going to be a bit longer than, it's going to be a bit longer than 60 minutes. Or maybe a bit longer than 90 minutes. We'll see. Is one-hot encoding used in loss function for binary cross entropy? Yes. As in your labels are one-hot encoded. I hope this should have been clear. If it is not clear, then maybe I've made a mistake in trying to explain this. So see, when I'm comparing my labels are one-hot encoded. Like if what one-hot encoded means is like you have them as 1 0 1 0 0, where wherever the label is 1, it just means that then that category exists. But if it's not one-hot encoded, then you have IDs, like you have horse represented by, say, class ID 2, or like you basically have class ID. So that's the difference, but you're definitely using one-hot encoding. And then you compare your predictions to that using binary cross entropy loss, which I explained. But Korean, could you maybe reply to this comment and let me know that this is clear, that we are using one-hot encoding? Because if this is still an issue, is this still an issue to people? Do you guys still not understand loss function? Because I hope it should be clear by now. Okay, I'm just gonna give Corinne some time. So then you can have your metrics as that accuracy multi with some threshold, and you can see how if I had a threshold of 0.1, my accuracy was 0.92. If I have a threshold of 0.99, my accuracy is 0.94. So you can see how it's important to pick up a threshold so we can get our predictions and we can get our targets. And then we can check the accuracy multi for like different thresholds. So I can then create a simple loop that will loop through these different thresholds. And then I can plot this chart that says, okay, for which threshold, what's my accuracy? So the nicest threshold seems to be like 0.6, where you get like 96.5, around that mark accuracy. So let's actually put it here and see what that is. 96.4, yeah, 96.5. So that's the accuracy. So that's how you pick a good threshold in multi-label classification. Cool. That's it for multi-label classification. Now let's go into regression. So what's the difference in regression? When we say regression, what's the difference in regression? And you would have seen regression mostly in terms of like linear regression, or like you would have used in terms of machine learning. Not deep learning is not very common, although that is changing still, but it's still far behind in terms of computer vision and NLP. So the data set that we're using in this one is this BV Connect head post data set. So I'm just gonna show you what it means. Actually, while that opens, it's much easier to just go through this. So let me just untar that. This is going to download that data set. That data set has like all of these different folders and then some objects. And then you can see how there's like all of these different files in the data set, the details of which aren't as important. But the idea is, in this data set, the data set basically looks like this. You have images of people, or basically like facial images, and then in this data set, the task is you're trying to predict the center of the face. So you're trying to predict coordinates instead of like yes, no, basically you're trying to predict a number. And when you're trying to predict a number, which is a float or like, it doesn't matter, it's a regression problem. And in deep learning then, because until now, all we've done is we've done classification, or we've looked at multi-table classification, but we haven't looked at how you could predict, how you could use the deep learning model to then predict a number. But if you think of it, I'm just going to make like a simple, I'm just going to say my model, right? Depending on however many classes or whatever I do, I could say like, I could classify using two classes. So one could be my X coordinate, one could be my Y coordinate. And then these are, the predictions themselves are always floats. Like these are always, the model's always predicting floats. Like it could be 101.2, this could be minus 7.3. Then I could treat these as coordinates. And if my actual coordinates are, say, 100 and say 50, then I could go y2 minus y1 square plus x2 minus x1 square whole under the root, which is root mean square error, or I could just use MSE without the root, without the square root. So that's just my mean square error. So I could calculate my loss function this way, is like find, because the main idea is I want this number to be close to this number, and I want this number to be close to this number. So if I go like y2 minus y1 square, I'm calculating whatever the difference between these two numbers is, and I'm going to try and minimize that difference. I'm just going to call it d, like the difference. And then I can, let me call it x delta x. So delta x just stands for, if this is my x1 and this is my x2, then delta x is just x2 minus x1 squared. Excuse me. And then I could do the same thing for my y. So I have my y1, y2, and I could calculate my delta y, which is just y2. I'm just calling it, the mathematicians, please don't be angry with me. But I'm just trying to make things simple. So then that's my difference. And what the loss function is going to try and do is it's going to try and minimize this difference. So when that happens, then you automatically, then you can train and use deep learning for regression problems as well. And that's the basic idea. There's not really anything that's different when you look at this FastAI notebook. So you'll see how there's some files, you can grab all the image files. So you have your image files, and you can see there's basically your labels are as part of that text file. You can create your image file, and you can have a look at this image. That's how the image looks like. It's not really important on how you get the labels, but there's this, if you really want to understand how we're getting the labels, go and have a read of how the data set is structured, and then you'll be able to see how the calculations of the center of the face or those coordinates can be calculated. FastAI book doesn't go into the details, and I won't go into the details of this either, but you can basically pass a path to your image file, and then that function will give you your X and Y coordinate. And that's it. That's the main thing. So you can use this as your get Y, because that becomes your label. So in this case, your label, instead of being like a category, it's just some number. My get items becomes my get image files. And of course, I have my image block. And instead of using a category block in FastAI this time, I'm going to use something that's a point block. So FastAI, if you use a point block, FastAI will already know that instead of doing classification, you're trying to do regression. So you're basically like going to predict numbers, and you're going to do all of this stuff. And then the splitter in this case, what happens is, because in the data set, you have images separated by folders. So the images are separated by folders. And then if you use a random splitter, then what's going to happen is like your train set is going to have the image of the same person. And then you're like, if there's like, let's say, if there's like, say, 5 people in the data set, 1, 2, 3, 4, 5, and each one of them have, say, 10 images. So this is a list of my 10 images. for the 5. And if I use a random splitter, then it's going to find this in the validation set, this part in the validation set, this part in the validation set, this part in the validation set, or this part. But that's going to be much easier for the model because it would have already seen the images of that person around it. But when you deploy this model or you want to use this model in a real case scenario, you're pretty much going to have things like you're going to have your training set of like people or faces, and then there's going to be, you're going to upload a new person's image. So it's much easier than to have your training set and validation splits split it this way. Is like your validation set is like a person with its own folder, which the model has never seen before. And that's what is happening here. You're just saying, okay, the folder name is 13. So don't use that folder in the training set. So my training set consists of people of different faces, and then my validation set is just that one person. So I can then now apply my transforms, and that's pretty much it about regression. I haven't personally used FastAI for regression a lot, or for point block, but recently I've started working on object detection and bounding box. In object, I'm just trying to explain the importance of what we've learned is like in an image, then not only do you have to classify the label, but you also have to provide the coordinates of like X, Y, X1, Y1, X2, Y2, so on. You have to like classify and provide these coordinates. And then in that case, what we learned today is when that will come in handy. But it's okay, have a read of this. Then you can create your data loader, you can show batch, you can grab your first batch, you can see the shapes. When you're trying to run this back, have a look at why these shapes are what they are. If you can't figure it out, ask on Slack channel. But then you can see, okay, that's my label, and then you can train your models straight away. You have your CNN learner, and you can say, okay, the outputs, please make the outputs to be in between this range. FastAI internally uses this function called sigmoid range. It does ask, like, why does this function convert, like, whatever my outputs are into the range that I defined between -1 and 1. I know I'm going very quickly over this section. I didn't mean to explain this part in detail, but I'm also trying to save time for the Cassava classification competition. So I'm just going to leave this with you guys. Have a read of this part of the section. It should be fairly simple, and it should be like what we've covered so far. There shouldn't be anything different in this part of the notebooks. And then you can just train your model, and you can see your results, and then the model's really trained pretty well. That's chapter 6. I know I didn't go in much detail in the last part of the notebook, but that's intentional. So do that in your own time, have a look, have a read. And if you still have questions, please ask on Slack or come back and we will cover this next week. So last questions. It was a bit unclear. Okay, I hope that's now clear and Brad's helped. So thanks for that. I want to understand the batch transforms for the data block. I want to understand the batch transforms of a data block object for regression task. Does it do the items transforms resize function in the batch transforms and then later normalizes? I do not know. I think that's a very FastAI specific question. I'm not sure. I don't have the answer. So have a look at the forums. Maybe asking on the forums would be a better place, or yeah, I think asking on the FastAI forums. So going to forums.fast.ai. That's definitely a better place for this question. I'm sorry I don't have the details and can't help you much there. What usually do you use for regression? Classical algorithm from scikit-learn? No, I don't. Depends on the problem I'm trying to solve, I guess. But then what I use for regression is very different to the problem that I'm trying to solve. Then I've been using that for object detection, but again, okay, as I say, that's deep learning, and then that's separate. So that shouldn't be something we should go into much detail today. So I'm going to skip over this question intentionally as well. All right, so that's that. Now we are going to the Kaggle competition. So we're doing the live coding part. So let's go to the Kaggle competition. All right. So now with Fast AI, what we're going to try and do is we're going to try and build a solution for Cassava leaf disease classification. As you'll read through this chapter, I'll give you some background. So cassava is basically a key food security crop grown by smallholder farmers. And this is mostly, you have some label images, so introduce a data set of like these plants or these leaves basically of that crop, and you have 21,365 labeled images. And it mostly comes from Uganda. The labels were done at this particular university, I guess. And then the task is to classify each leaf image into the 4 disease categories or a 5th category, indicating a healthy leaf. So there's like, you could think of like, there's like these 21,367 images, and each image either has like a 4 disease category, which we'll look at what those diseases are, but basically then each image has 4 diseases, or there's like a healthy leaf. So you can think of it like being like a problem where you have to classify every image based on the 5 categories that you have. So this is not very different from, in fact, it's very similar to the pets data set that we looked at. You have an image. Instead of having 37 classes as in pets, you have 5 classes. So if you have a look at the data, you can see how enable to show preview. Okay, please download it. Oh, I already have it. Okay, no worries. I can download it again. Train Cassava. It should be double S. Anyway, so if you have a look at this train.csv, you'll see how for every image ID, you have 1 label. So it's single label classification, the problem. It's not multi-label, it's single label. So yeah, so you have like a long list of image IDs, and then you have the labels. So that's your training set. And then as for which image, or like what does the leaf or like those numbers in terms of labels 0, 1, 2, 3, 4 represent? 0 represents this disease, cassava bacterial blight. So if I search for that, if you need some background, you can read about it. Like you can see how does it spread, or you can have some background information about this task. But for me, I'm not worried about what these diseases are for now. What I'm worried about is the task that I have at hand is I have these images, and what I want to do is I want to classify them to these 5 labels. Basically the 5th being the healthy one. And I want to use Fast AI, and now I'm trying to find solutions on how I could do that. The thing that comes to my mind is just to follow the pets tutorial or the pets notebook and try and see if I can use that to build a solution. So I don't have a solution handy. I didn't do this before. I actually wanted to keep it as raw as possible. The only reason being that we can then run into problems. The only thing I've done is I just have my Cassava folder, and in that I have a data folder. And what I did was I downloaded that zip file, which is basically I downloaded this data set using this Kaggle competitions download command. If you try and run this in Google Colab, that should also work. So what we do right now would also be the same steps in terms of like Google Colab. In Colab, you'll only have to run this command every time, or like download this data set every time you rerun the notebook. But all I've done is I've downloaded the data set in my data in my data directory, and I have my train images, my test images, and everything here. So all that's on Kaggle is now available for me to work with on my computer. And then I've just created a new folder called notebooks, which is empty. And we're going to use pets. Basically, we're trying to follow the pets template. So I'm just going to call it, let's call it Cassava baseline. And the reason why I wanted to show you this is, yeah, it's basically when we work on a new kind of a problem, then you're going to run into different challenges. And that's where the main learning is. So from going forward from today, I want everybody to try their hand at new problems. So let me bring up the Fastbook chapter pets. Here it is. And then we're just going to follow everything that we did for pets and try and see if that works for Cassava. Okay. So first thing, I don't want to use Fastbook. I'm just using fastai.vision.all, import star. Thank you. Let's see, I'm just going to use the tree command. And I'm just going to see how. So what tree does, it will just say, okay, these are the folders. So I'm basically running bash in my Jupyter notebook. So let me then, based on this, define my paths. So my data directory is /data. My train directory, or where my train files are, is my data dir / train images. My test dir is my data dir / test images. And then let's just make sure they look right. They do, perfect. Then I guess instead of like using the tree command, you could have also done something like this in FastAI, data.dir.ls, which will show you, okay, these like 8 things in there. You have a train TF records folder, there's a sample submission CSV, there's Cassava, leaf disease, zip, you don't need to worry about this. We can delete this, but then basically, yeah, that's another way of doing the same thing. All right, so that's the first thing that I've done. Now, what do I want to do next? I want to have a look at how does this train.csv look like. So next step is just going to call, I'm going to use pandas. So we looked at it last time. So pd.readcsv, that, and then I can call head, and I can see, okay, that looks correct. Like I have my image ID, I have my label. All right, now in pets, what we did was, so we have untar data. That's basically downloading the data from Kaggle and then having it in a path. So we already did that. I kind of showed you path.ls. Okay, let's try this path. So my train dir, that's where my images are, .ls. So okay, so that's 21,397. How many did Kaggle say there are? 21,367. So okay, maybe either this is wrong or this is wrong. I guess we'll find out. But it is a close number, so I'm fine with that. So then, okay, I can see my folder has images, which is good. The images are like, this is the image and all end with JPG. So that's fine. And then that's just using file name. I don't need to worry about that. I don't need to worry about that. And then they build the data block in pets. Okay, without building the data block, what can we do next? So I've had a look at my stuff. There's a function I can use so see how the data block is using get image files as the get items. Let me show you what this get image file does. So let's say my Cassava image file paths are get image files in my train dir. Okay, that's perfect. So what this get image file does is like, it goes in that train dir, which is this directory, /train images. That's where my data, or that's where all the images are. And then it will only grab the image file. So we've looked at this in the past. I won't go into the details, but it will only grab the image files. So that's how many image files I have. Now, one thing I want to do is if I check the shape of my, basically my CSV, it's the same shape as the number of files I have. That is good, because that means then for every image, I have a label. So far, so good. And then the next thing in my head I want to do is I want to check how many images per each label there are. So if I do something like this, it will tell me, okay, the most number of images I have are for label 3, and then every other label is 1, 2, or 4, or like around 2,500, and then 0 is 1,000 images. So what does this tell me? This tells me my data set is imbalanced. And I'm trying to show you, so see, so far we haven't worked with the data set that is imbalanced. So what we need to do is for a good solution, we need to be able to find a way to either add weights to my loss function. We need to find a way to balance this data set. That's what I'll say. And then there's like different techniques to balance a data set. I won't go into the details, but you could add weights to you could basically add weights to your loss function, which means when your model's trying to classify, or when the loss is being calculated, every time you make a mistake on the rare classes, it's going to cost, or the loss is going to be higher compared to when you make a mistake on the class that has more number of images. So there's like different ways. There's also things like oversampling, undersampling, and like all those other stuff, which you will find, I believe, in the discussion part of this Kaggle competition. So that's the reason why I wanted to show you this, and I wanted to involve everybody. The Cassava leaf disease classification and Kaggle in general is, now you're trying to see like this challenge, and then you can read the previous solutions on how people did it, and then try and replicate that using FastAI. So that is a really good way to learn, and that is a really, really good way to then become a better practitioner and just get better as we go. So that being said, okay, that's the main thing. Now, the first thing I'm going to do, as I've told you, is I'm going to try and build a baseline. What does that mean? It means no tricks, just a simple working model. I don't care about imbalanced data set, corrupt images, or anything for that matter. I am just going to apply what I know and see what accuracy or what validation metric I get. So what does that mean? That basically means this is our first iteration. Remember when we were talking about FastAI in, I guess that was chapter 2, when you're trying to put things in production. We're not trying to build a perfect solution right from the start. We're trying to build a really bad, or like whatever I know, I'm trying to build a really easy, low effort solution. And we will get some accuracy, and then, or we will get some validation metric value. And then that's where we try and improve it by adding like new things. So that's how I like to work on these things, and rather than spending lots of time on, and that's what the FastAI kind of recommends. So that's the basic thing. So now what I need to do is I need to be able to convert this training data frame into a data block. So let's copy this, right? Because it's gonna look the same. So my first thing is an image. My second thing is a category. That's right. I can use the get image files, which returns those 21,000 parts, which is perfect. In terms of splitter, random splitter is fine. I don't need to worry about things. Oh, get why. This will need to be updated because now I'm not using regex anymore. What I'm going to do, so what the FastCI, as I've already said in the past, is like it's going to basically whatever your get items is. So this is my get items. So whatever that returns, this thing's being returned. For each path, you're going to extract your X and you're going to extract your Y. So now I need to be able to define get Y so that that path gets converted to a Y label. All right, so I have a path. My Y label is in this train DF. So how could I convert this path, whatever this image path is, to then this label? Easy. What I could do is I could grab the file name of this path. Then I can go in this train DF and I can find the corresponding label to that file name. So let's do that. I have my path. So my file name. So actually, I'm going to show you my image files. Oh, okay. That's not defined yet, is it? Did I store my get image files output anywhere? I did. Cassava image file paths. So I have my Cassava image file path that returns a path. I can call a name function on this path. So remember, path lib path. When that returns a path, it's just an object of this path lib path type class.
Aman, your mic got muted.
Oh, I'm so sorry. What was the last thing I said, Angelica, before muting myself?
Something about the path.
Okay, thank you. My bad. Thanks, everybody. All right, so I think I was just showing you, then I'm going to use the name attribute to grab my file name. So I can, if I apply that name attribute, if I use that F name, then I have, this is my file name. Now I can use this file name to search for the corresponding label in my train DF. So I can go, I'm going to use pandas now, train df.query. I'm going to query my data frame. And I'm going to say, find me the row where image ID is equal to this F name value. And you can see, okay, there's the row. All right. And that label is 3. All we care about is this 3 dot. So we grab the label, which gets returned as a series. So I can convert that to a NumPy array or the value that I want, and then I can just grab the value from here. That's a really bad way of grabbing the value, but hey, it works, and we only care about a baseline. So in a baseline, all we want to do is build a pipeline that works. All right, so then this is it. This is how I can grab my label. So my file name becomes, I'm just going to now use it here. My file name becomes that path.name. And then I can use this return train df.query image ID equals fname.labels.values.1. Perfect. So let's see if that works. Get Y on my Cassava image files, that it works. It gives me the correct, gives me a label for that path. So I've been able to convert things to a label. Excellent. Are all of those? No, yeah, okay. One thing I could also do, I think there's a attribute. So I'm just showing you something extra. Oh, dot map. Is that what it is? I'm not sure how things work in list in the FastAI sort of world. Would that work? I don't know. It's taking too long. Never mind. I'll show that sometime after. I was just trying to apply this function to FastAI. So let's see, FastAI. Actually, why leave it? Let's have a look. That's a challenge that I have, and let's try and find a solution for it. So what I want to do, the problem is, now I've been able to apply this function to one of the parts, but the Cassava image file parts is actually a FastAI list of that many files. So I just want to see, I want to apply this getY function to each of the parts so I can grab the label for each of these parts. So let's see if there's, what are the methods in FastAI docs? Okay, there is a map. What does L.map do? Create new L with F applied, with the function F applied to all the items. That's exactly what I want. So let's do that. It's just this time, let's just say my labels from parts equals, let's apply it to just the first five parts, so it's not very slow. Let's see if that works. Oh, it does. Here we go. My first five parts look like that. And then I've just been able to convert those into labels. Perfect. So we're able to get the labels from the part. Now I can, now you could just apply it for all of the parts, and that's how it works. I guess I wanted to show this because I didn't know how to do this myself either. Like I had some idea, but I didn't know. And when you're working on new problems or new challenges or new solutions, you'll also get into these situations where you only know so much, right? We only know things about the pet breeds, but everything in the world is not going to look like pet breeds. Things are going to look like Cassava, or things are going to look a bit different. And then documentation for the different libraries is your friend. So that's why you're going to follow the same process. Is like you want to go read the documentation, and then you'll try and find a solution for the problem. Okay, so far then, that's fine. So I can just say copy paste this get Y over here. Item transforms, let's not touch anything. Let's not touch anything. Let's just call this Cassava, and then my data loaders become Cassava.data loaders. Instead of passing a path / images, I already know where my train images are. So that's that, train dir. Let's see if that works. It's running. There's no error as such, which means things are probably running. Things are probably going okay. While that runs, let's see if there's any questions. Where are you, my Weights and Biases forums? That's still running. That's running too long. Now I'm scared. Let's see if there's any questions so far. One other thing I like to do before getting a baseline even is just to see what my accuracy would be if I use the same prediction for all the values. So in the case, if you predict everything is a 3 with 100%, that gives you the lower bound. Okay, thanks, Kevin. That's actually a good idea as well. So what Kevin's saying, like, just make the label be everything as a 3, and then you'll see like you can't go any worse than that, right? Okay, so that worked. So I now have my data loaders. I can now say show batch. Let's see if that works. DLs.showBatch works. Oh, nice. Now I have a corresponding label for each of my image. Let's see how many there are in my train. What's the length? I just need to find the length in my data set. So that's around 17,000. Did I miss something again? I keep calling it val. Okay, so now FastAI, based on this random splitter, has done a 20% split for us, which means it's put 17,000 files in training and it's put 4,200 files in validation. So that's it. Now, remember when I told you that as long as you get the data loader working in FastAI, things are done, things are solved. So happy days. All we now need to do is, where is it? All I now need to do is I have my data block working. I have my data loader working. I don't need to worry about the loss function. All I need to do is define a learner. So let's see how we define the learner. It's already been defined. Here it is. So now I can say, please define my learner. I can pass in my data loaders. I can pass in a model, ResNet 34. In terms of metrics, because we are calculating accuracy, it would be nice to have a look at this. I can do this, my learner. And then, because I'm only calculating the baseline, I could just call learn.finetune, but something that we touched last week is LR Finder. So let's try and find a good learning rate for this problem. While that's running, I'm going to go back and see if there's any questions so far. No questions. Very good. So that's going to run and run. So we already know what that's doing. And it gives me a suggested learning rate. So you can see how that curve looks like. So let's use that learning rate, which is 1e neg 3. So I can say learn dot fine tune, and I can say 5 epochs. Where's my learning rate? Base LR as 1e neg 3. So instead of actually fine, let's just say 3, just so that runs and finishes. Cool. And guys, there we go. We have a baseline working for Cassava competition. And now my model's already training. So the next step is now what we really want to do, once that finishes, what we could do is we really want to check how we show up on, like, if I use this, of course, we're going to have our validation metrics. It's going to provide us, when I say validation metrics, it's just going to say how well we performed on the 4,279 images that the model did not see. So we have like 30% error rate, which means in the very first epoch, our model is 70% accurate and it's able to classify the images, which is pretty good. Like we haven't, how many lines of code did we write? We wrote like majority we just did, we defined a get Y, about like, I don't know, 20, 25 lines of code. That's the maximum, including everything that we've done. And we're already able to create a Cassava leaf classifier, which is an actual product out there in the world. And the best that people can do is 90%. And they would have spent like a lot of time in getting 90%. But in 10 minutes or 20 minutes, we're able to already get 70% in our very first epoch. So I think that's a really good result. And in fact, we're actually now able to get around 78. So when that finishes, you'll see how what my error rate is. Then the next thing you want to do is, I actually didn't do this either. So I can now go and click on late. Oh, you do not have any Kaggle notebooks. I'm out of my Kaggle GPU memory, actually. I've used all my GPU, so I can't really do a submission right now. Yeah, turning on GPU availability, quota resets. Yeah, I've used all my, I should have thought of this. I've basically used all my GPU quota on Kaggle because I'm participating in a competition. What's the best way? What I want you guys to do is then go back and actually, I know what's the best way. Let me, where is this? Where's my image? I'm going to create a same validation set for all of us. So this is that, right? That's my train DF. Oh, this needs to stop. Please stop. Yep. I already have my train DF defined. Train DF dot head. Okay, that's my train DF. How about how do you even shuffle things in pandas? I've not used pandas in a long, long time. So let's see how we shuffle things in pandas. I could have used np.random, but I just want to use pandas shuffle data frame. Let's see how we can do that. How to shuffle a data frame? Is there any documentation to? All right, let's just try. Then the next thing I like to do is just use shuffle. If that didn't work, so let's see how that. Let's have a look at a Stack Overflow. What does it say? Oh, there's a sample. Of course, that was the sample. So I can say sample, and my frac is going to be 1, which means basically permute my whole data set. So that's that. And then I'm going to say reset index drop equals true. And then I've just shuffled my data set. I'm just randomly shuffling. I could have used the fast AI splitter. Actually, that would have been nice. Never mind for that for now. So I've just shuffled my data set. And what's the length train df? It's 21,000. So I'm just going to say train df. I'm going to add a new column is val equals false. So now I have a new column is val equals false. And then let's see if I can grab the 20% of my data as the validation set. That's 4,000 files. Let's just grab, you'll see how slow I am. Let's just grab the last 4,279 files and grab the second column. So then that's all false and set it to true. And then let's see how that looks like. That's perfect. Is val.value counts. All right, so there's false for around that number of files and true for around that number of files, which is great. And now train df.csv 1 db Cassava train val split.csv index equals false. So let's see, did that work? Where was I running this notebook? Kaggle Cassava cd, oops, cd // Kaggle Cassava. Do I have that file here somewhere? I do. So let's create a Kaggle dataset. I'm just going to call it Cassava train test split. Move 1 db to Cassava train test split, cd Cassava that. And then let's call Kaggle datasets. In it, I'm just initializing my dataset. All right. That creates a file. I'm just creating a data set for you guys, just so you guys know what I'm doing. I'm creating a data set. So both of us have the same train test split. So let's call this title 1 db Cassava train test split. Let's call this 1 db Cassava. And then Kaggle datasets create p dot. Starting upload, excellent. So that will create that data set. Now, okay, what I've done is I've created this data frame, which has the image ID, the labels, and the is validation false or true. Okay, so what we learned today in Fastbook in multicat is that it was multicat, right? Where we had a is val column. When that opens, actually it's open here. So we can now define our custom splitter. So I just want to show you what you want to do this week. So this week, I'll tell you, oh, sorry, 1 second. Yeah, the splitter is this one. All right, that's what I want to do. So when you go, instead of like having things like this, have your, instead of like passing random splitter, I'll rerun this notebook and show you what exactly you have to do. So when you go back this week, do this. Import, download the data set, but also download this file. Where is this? Data sets. I will share this with everybody on that W&B forums. Download this dataset file. W&B Cassava train test split. Download this file. You'll see over here, there's like this W&B Cassava train test split, which is val false or true 20% of the time. So let me post that link on the forum and also in the chat. So I want everybody to go back, download that file on your respective computers or Google Colabs. So I'm just going to post it here. You need to save traindf back to. Oh, I did in place. I did do in place equal to true. Did I not do that? 1 second. Sorry. Kevin's pointed out something. Traindf.sample. Oh, that's right. I didn't. But that's okay. That shouldn't be a big issue. That's fine. Sorry, Kevin, and thanks for pointing that out. That's a good point. Anyway, you go to that link, then you will download that CSV file, and then use the same train and validation split as in that file. How do you do that? You define this sampler. So I'm just gonna go and show you. So when you have the file, do it like this, do it like this. Instead of like reading the file from the notebook, read the file that's this train test split CSV file. Okay. So that becomes your training def, a train df, and now you're gonna have isval, and you're gonna have and now what you do is you use this splitter. So you have the same splitter, which means train df, basically my df.index, df is valid to list, and then that. Yeah, that's perfect. And then just pass this splitter to your, when you're building your, follow the exact same thing so far. Instead of using a random splitter, pass that splitter. And now what that will do is do exactly the same steps. And what that will do is each one of us will have the same training and validation split. And then go back and try and beat, what's the accuracy I got? I got like 80% and it's still running, but I got like 80% accuracy. So go back and try and beat that accuracy of like 80%. Try and have your accuracy go up as high as 85. The ways to do that would be try a different model, try a different learning rate, try going through the fast Cassava discussions. You can also have a look at the Kaggle notebooks. You will see there's lots of fast AI starters. So if you search here, fast AI, you'll find like there's already lots of solutions. There's few from Zach, which already has scores like 0.892, which is really good accuracy. But have a read of all of these different things of fast AI and try and break this, try and beat whatever this 80% accuracy is, and then just post it on this discussion forum. The data set looks private. I'm really sorry for that. Let me try and make that up. Let me update that. Thanks everybody for pointing out these things. As you can tell, I haven't done this before, and hence so many problems. But thanks guys for bearing with me. Okay, it should be public now. That should work. All right. So do all these steps, go and download that file, and then run this and post your accuracies with me. Write your blog post about this this week. That's the homework. The homework is work on Cassava and beat that 80% accuracy. Any questions? No questions? Anybody wants to put anything in the Zoom chat or anywhere? Or is everything good so far? Okay, there's nothing. Thanks, Kevin. I didn't enjoy it at all though, but I'm glad you did. Probably you had a good laugh, but that's all good. Cool. Thanks everybody then. I will see you guys next week. But for this week, come to this W&B forums, come to this discussion, and post your accuracies, post your blog posts, share them with me on Twitter, and then we'll recommence next week, or let's just chat throughout the week on what are the things you've tried, what are the things you haven't tried, what are the things you'd like to try, and then let's keep this project going week after week. Let's try and work on the Cassava leaf classification for around 5 weeks, maybe, or 3 weeks, or around that time. And let's try and actually get a really good accuracy. And each one of you then have a project to showcase on your resumes. So thanks, everybody, and see you guys next week. Bye.